When we look up at the night sky, every star, planet, glowing nebula, and distant galaxy that we can observe represents only a tiny fraction of what actually exists in the universe. Everything we can touch, see, or detect with our most advanced telescopes, the entire periodic table of elements, from hydrogen to uranium, makes up approximately 5% of the mass-energy budget of the cosmos. The remaining 95% is entirely invisible to us, split between two mysterious phenomena known as dark energy and dark matter. Dark energy accounts for roughly 68% of the universe and drives its accelerated expansion. Dark matter makes up about 27%. This means that dark matter outnumbers the matter that makes up you, me, and every star in the sky by a ratio of roughly 5 to 1. To understand dark matter, we must first clarify what astronomers mean when they use the word dark. In everyday speech, something is dark if it sits in a shadow or fails to emit light. Charcoal is dark, but if you shine a flashlight on it, it reflects light. If you heat charcoal up, it glows red. Dark matter is fundamentally different. It does not reflect light, absorb light, scatter light, or emit light across any portion of the electromagnetic spectrum. It is completely invisible to radio waves, infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. A more accurate term might be transparent matter or invisible matter. It does not interact with the electromagnetic force at all. The primary way we know it exists is through its gravitational pull on the ordinary matter that we can see. The story of dark matter begins in the 1930s with a Swiss-American astronomer named Fritz Zwicky, who was working at the California Institute of Technology. Zwicky was studying a massive cluster of galaxies called the Coma Cluster, located over 300 million light-years away. A galaxy cluster is a bound collection of hundreds or thousands of individual galaxies, all orbiting around a common center of mass. Zwicky wanted to measure how fast these galaxies were moving and estimate the total mass of the cluster. To measure the speed of the galaxies, Zwicky used the Doppler effect. Just as the pitch of siren changes as an ambulance passes you, the frequency of light shifts toward the red or blue end of the spectrum, depending on whether a galaxy is moving away from us or toward us. Once he measured these orbital speeds, he applied a standard principle of classical mechanics known as the virial theorem. The virial theorem relates the total kinetic energy of a system in equilibrium to its gravitational potential energy. In simple terms, if you know how fast objects are orbiting in a bound system, you can calculate how much mass must be inside that system to keep those objects from flying off into deep space. When Zwicky completed his calculations, he encountered a staggering discrepancy. The galaxies in the Coma Cluster were moving far too fast. Based on the light emitted by the visible stars and gas in the cluster, there was nowhere near enough mass to generate the gravity needed to hold the cluster together. According to the laws of physics, the Coma Cluster should have torn itself apart billions of years ago, with individual galaxies flying off in all directions. Yet the cluster remained intact. Zwicky concluded that there had to be a vast quantity of unseen mass providing the extra gravitational glue holding the cluster together. He called this mysterious substance Dunkel Materie, the German term for dark matter. Because Zwicky had a reputation for being somewhat eccentric and abrasive, and because astronomical measurements at the time carried large uncertainties, the broader scientific community largely ignored his finding for nearly 40 years. Most astronomers assumed that either the measurements were incorrect or that the laws of gravity worked differently on massive intergalactic scales. The breakthrough that forced the scientific world to take dark matter seriously came in the 1970s, led by the American astronomer Vera Rubin, alongside her colleague Kent Ford at the Carnegie Institution of Washington. Rubin set out to study the rotation curves of individual spiral galaxies, starting with our neighbor, the Andromeda Galaxy. A galaxy rotation curve is a simple graph that plots the orbital speed of stars and gas against their distance from the galactic center. In our own solar system, the orbital speeds of planets follow a predictable pattern defined by Keplerian dynamics. The Sun contains more than 99% of the mass in the solar system, so the inward gravitational pull drops off rapidly as you move outward. As a result, Mercury orbits the Sun at nearly 47 kilometers per second, while distant Neptune orbits at just 5 kilometers per second. Astronomers naturally expected spiral galaxies to behave the same way. Most of the bright, visible light in a spiral galaxy is concentrated in its central bulge. Therefore, stars near the outer edge of the galactic disk should orbit much slower than stars near the center. Using an exceptionally precise spectrograph built by Ford, Rubin measured the optical spectra of gas clouds across spiral galaxies. What she discovered shattered expectations. As she measured points further and further from the galactic center, the orbital velocities did not drop off at all. Instead, the rotation curves remained completely flat. Stars at the extreme outer edges of spiral galaxies were orbiting at virtually the same speeds as stars close to the bright central core, typically between 200 and 250 kilometers per second. If the only mass in these galaxies was the mass we could see in the form of stars and gas, those outer stars should have been hurled out into intergalactic space by centrifugal force. The fact that they remained comfortably in orbit meant that galaxies were surrounded by immense, invisible reservoirs of mass. Rubin showed that spiral galaxies were not self-contained islands of stars, but rather tiny visible centers embedded within vast, spherical halos of dark matter. These dark matter halos extend far beyond the visible boundaries of the galaxy's spiral arms and contain up to 10 times more mass than all the visible stars combined. Rubin's meticulous observations were replicated across hundreds of galaxies, establishing the dark matter problem as one of the central puzzles in physics. Yet, galaxy rotation curves and cluster dynamics were only the beginning. Over the past 50 years, entirely independent lines of observational evidence have converged on the exact same conclusion. One of the most powerful modern tools for mapping dark matter is gravitational lensing, a phenomenon predicted by Albert Einstein in his general theory of relativity. General relativity tells us that mass warps the fabric of space and time. When light travels past a massive object, its path is bent by this spatial curvature, much like light passing through a glass lens. When astronomers look at a distant galaxy located behind a massive galaxy cluster, the cluster acts as a gravitational lens, bending and magnifying the light from the background galaxy. By carefully analyzing the distortion, arc shapes, and multiple images produced by gravitational lensing, astrophysicists can construct a detailed map of the mass distribution within the foreground cluster. These lensing maps consistently reveal that the total mass required to produce the observed light bending is vastly greater than the mass of the luminous stars and gas. Crucially, gravitational lensing relies purely on geometry and the warping of space. It does not depend on assumptions about orbital mechanics or stellar brightness. It provides a direct, non-dynamical measurement of total mass. Perhaps the single most compelling piece of evidence for dark matter comes from an extraordinary cosmic collision known as the Bullet Cluster, cataloged as 1E0657-558. The Bullet Cluster consists of two giant galaxy clusters that slammed into each other at high velocity billions of years ago. As the two clusters passed through one another, the individual galaxies within them hardly interacted at all, simply gliding past each other because galaxies are mostly empty space. However, the diffuse, superheated gas that fills the space between galaxies, which constitutes most of the ordinary baryonic mass in a cluster, collided head-on. Electromagnetic interactions caused this gas to slow down, drag, and heat up dramatically, creating a distinct central region visible in X-ray light recorded by the Chandra X-ray Observatory. At the same time, astronomers mapped the total mass distribution of the colliding clusters using weak gravitational lensing. If mass was concentrated where the ordinary matter lived, the gravitational lensing map should have centered directly on the hot, X-ray emitting gas in the middle. Instead, the lensing maps revealed that the vast majority of the mass had passed right through the collision without slowing down, leaving the hot gas behind in the center. The invisible mass had decoupled from the ordinary matter. This observation provided a smoking gun for dark matter. It demonstrated that dark matter is not merely an illusion caused by a misunderstanding of how gravity operates on large scales. It is a physical, collisionless substance that passes right through other matter without experiencing electromagnetic drag. To understand where dark matter fits into the history of the cosmos, we must look back to the very beginning, the Big Bang. About 380,000 years after the universe formed, it cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely across space for the first time. We observe this light today as the cosmic microwave background, or CMB. The cosmic microwave background is a nearly uniform snapshot of the early universe, displaying tiny temperature fluctuations of only 1 part in 100,000. These tiny fluctuations reflect small density variations in the primordial plasma. By analyzing the power spectrum of these temperature ripples, specifically the relative heights of the acoustic peaks, cosmologists can measure the physical density of ordinary baryonic matter and dark matter in the early universe with exquisite precision. The CMB data reveals that ordinary matter could not have formed the cosmic structures we see today on its own. In the early universe, ordinary matter was tightly coupled to light through electromagnetic radiation. The intense pressure of light smoothed out concentrations of ordinary matter, preventing them from collapsing under gravity. Dark matter, on the other hand, did not interact with light. Long before ordinary matter could clump together, dark matter was already collapsing into gravitational wells under its own gravity, creating a hidden cosmic scaffold. Once the universe cooled and ordinary matter decoupled from light, it fell into the pre-existing gravitational potential wells formed by the dark matter. Without dark matter acting as an invisible structural foundation, there would not have been enough time in the 13.8 billion year history of the universe for stars, galaxies, and planets to form. We owe our very existence to the gravitational groundwork laid by dark matter. This brings us to the ultimate question: what is dark matter actually made of? Over the decades, scientists have systematically eliminated candidate after candidate. First, we know dark matter cannot simply be cold interstellar gas, dust, or unattached rocks. If it were made of gas or dust, it would absorb and re-emit radiation, obscuring background starlight or emitting thermal infrared radiation, which our instruments would easily pick up. Second, scientists investigated whether dark matter could consist of massive, dim objects made of standard atoms, known as massive compact halo objects, or MACHOs. MACHOs include rogue planets, brown dwarfs, cold neutron stars, and stellar mass black holes drifting through galactic halos. To test this hypothesis, astronomers conducted large-scale sky surveys looking for gravitational microlensing events. When a MACHO passes directly in front of a distant star, its gravity briefly magnifies the background star's light. After monitoring tens of millions of stars over many years, researchers found far too few microlensing events to account for dark matter. MACHOs can compose only a tiny fraction of the required mass halo. Third, we know dark matter is not composed of ordinary neutrinos. Neutrinos are fundamental particles with extremely small masses that interact only through the weak nuclear force and gravity. While they fit some criteria for dark matter, standard neutrinos are produced with vast amounts of energy in the early universe, moving at speeds close to the speed of light. Physicists classify such fast-moving particles as hot dark matter. Hot dark matter travels so fast that it streams out of small density variations, smoothing them out. If dark matter were hot, large cosmic structures like superclusters would have formed first, fragmenting into smaller galaxies later. However, cosmological observations show the opposite. Small structures formed first and merged to build larger ones. Dark matter must be cold or warm, meaning it moves relatively slowly compared to the speed of light. Today, the scientific consensus points toward non-baryonic, subatomic particles created during the extreme conditions of the early universe. The leading theoretical framework is cold dark matter, and several particle candidates are currently under active investigation. The most famous candidate for decades has been the weakly interacting massive particle, or WIMP. WIMPs are hypothetical elementary particles that carry a mass roughly 10 to 1,000 times heavier than a proton. They are predicted to interact only via gravity and the weak nuclear force. WIMPs are particularly attractive because of what physicists call the WIMP miracle. If a generic heavy particle exists in nature with an interaction strength typical of the weak nuclear force, standard thermodynamic equations show that the surviving density of these particles after the Big Bang matches the observed density of dark matter in the universe today. Supersymmetry, a theoretical extension of the standard model of particle physics, naturally predicts stable particles with precisely these properties. Another prominent candidate is the axion. Axions are ultralight, hypothetical pseudo-scalar particles originally proposed in the late 1970s to solve the strong CP problem in quantum chromodynamics, which explains why the strong nuclear force does not violate certain spatial and charge symmetries. Though individual axions would be extraordinarily light, trillions of times lighter than an electron, they could have been produced in immense quantities in the early universe, behaving as a cold, coherent Bose-Einstein condensate that acts as dark matter. Other theoretical possibilities include sterile neutrinos, heavy right-handed neutrinos that interact solely through gravity, and primordial black holes, which could have formed directly from high-density fluctuations in the first fraction of a second after the Big Bang, before nucleosynthesis began. To identify the true nature of dark matter, scientists are pursuing a three-pronged detection strategy: direct detection, indirect detection, and collider production. Direct detection experiments aim to observe a dark matter particle colliding directly with atomic nuclei in a laboratory setting. Because these interactions are extraordinarily rare, these experiments must be placed deep underground, beneath mountains or in disused mines, under thousands of meters of rock shield to block interference from cosmic rays. Detectors like the Lux-Zeppelin experiment in South Dakota or Xenon-NT in Italy use multi-ton tanks of ultra-pure liquid xenon surrounded by light detectors. When a dark matter particle drifts through the detector and bumps into a xenon nucleus, the subtle recoil creates a tiny flash of light and a small electric charge. While these experiments have set stringent bounds on dark matter properties, an unambiguous direct detection signal remains elusive. Indirect detection experiments look up into space for the secondary byproducts of dark matter collisions. If dark matter particles are their own antiparticles, or if they decay over time, two dark matter particles colliding in regions of high density, such as the center of our galaxy, could annihilate each other, producing pairs of high-energy gamma rays, positrons, or antiprotons. Space-based observatories like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station continuously scan the heavens for anomalous signals that cannot be explained by known astrophysical processes like pulsars or supernova remnants. The third strategy is particle creation using high-energy particle accelerators like the Large Hadron Collider at CERN. By smashing protons together at near-light speeds, physicists hope to recreate the high-energy conditions of the early universe and generate dark matter particles directly. Because dark matter particles would pass right through collider detectors without interacting, scientists look for events where the energy and momentum of the collision products do not add up, a signature known as missing energy. While particle searches continue, it is worth asking whether we might be thinking about the problem incorrectly. Is it possible that dark matter does not exist and that our understanding of gravity is simply incomplete? In 1983, Israeli physicist Mordechai Milgram proposed an alternative hypothesis called modified Newtonian dynamics, or MOND. MOND suggests that Newton's second law of motion and law of universal gravitation break down at extremely low accelerations, such as those experienced by stars in the outer rims of galaxies. By modifying gravity at low accelerations, MOND successfully reproduces the flat rotation curves of spiral galaxies without needing extra dark matter. However, while MOND handles individual spiral galaxies reasonably well, it struggles significantly on larger cosmic scales. It fails to explain the dynamics of galaxy clusters without adding extra unseen mass, cannot account for the gravitational lensing observed in the bullet cluster, and cannot reproduce the detailed structure of the cosmic microwave background power spectrum. Consequently, while modified gravity theories remain an intriguing area of theoretical research, the vast majority of astrophysicists view particle dark matter as the far more complete and robust explanation for the full range of observational data. Dark matter presents us with a profound cosmic irony. It is the dominant gravitational force that sculpted the universe, guiding the assembly of cosmic webs, galaxy clusters, stars, and ultimately the platforms where life could emerge. Yet, it remains entirely hidden from our direct perception, interacting with us only through the silent, invisible pull of gravity. We stand at a remarkable moment in scientific history. We have constructed a precise, quantitative cosmological model that can map the history of the universe across nearly 14 billion years. Yet we must humbly admit that we do not know what 85% of the matter in that model is made of. The search for dark matter is not merely an esoteric puzzle in physics. It is a fundamental quest to understand the underlying substance of reality. Whether the answer comes from a deep underground laboratory, a space telescope, a particle accelerator, or a revolutionary theoretical insight, unraveling the nature of dark matter will open a brand new chapter in our understanding of the cosmos.